Hello everyone, welcome back to the YouTube channel of Quest GIS. I again would like to thank all of you for supporting our work. This channel forms a platform for free education in GIS technology. So you can go to the various playlists which will help you understand and learn GIS technology using QGIS from the very basics. And if you are new to our channel, please subscribe and press the bell icon to get the latest notification on our latest uploads. And if you are interested in getting started with the basics of QGIS, you are in a perfect place and you can go to our channel and check out the different playlist. So in the previous videos of this morphometric analysis series, we discussed about SL index, which is a very important morphometric parameter for drainage basin analysis. And in this video, so this video you can say is one of the many videos in morphometric analysis series on this channel, where you will learn the basics and step-by-step method for calculating hypsometric analysis. Hypsometric analysis, again, a very important parameter for drainage basin analysis, and this we are going to learn through using open source QGIS processing toolbox. So hypsometric analysis basically includes calculation of hypsometric curves and hypsometric integral. There are different ways of calculating these two parameters, which we will discuss in this in the series of videos. So let's get started and build our theoretical understanding on the concept of hypsometric analysis first. Then we will move to QGIS and we will learn different methods involved in its calculations. Okay, then we will proceed to hands-on exercises. So as I said, there are two ways of understanding hypsometric analysis. First is hypsometric curves. So the diagram you see on the right side are hypsometric curves. Okay, so these hypsometric curves basically shows area and elevation distribution. Okay, so the area is plotted uh, on the x-axis and the heights are plotted, or the elevations are plotted on the y-axis. So basically hypsometric curves involve examining how the horizontal cross-section area of a landmass is distributed in relation to its elevation. Okay, so you see these are the elevations, and this is the horizontal cross section. So how this area, cross section area of a landmass, is distributed in relation to its elevation. And this study is depicted graphically, okay, by plotting the cross sectional area of the investigated basin against its corresponding elevation. And we will understand this in a very easy sense, okay, and what it signifies ultimately and why we need to calculate it, that we will understand one by one. This was just some scientific, technical thing that you should understand. Okay, so basically what we are doing here, we are taking the cross sectional area at some place and what is the elevation at that place. Okay, so we are doing this examination repeatedly in downstream direction, okay, in within a drainage basin. So this gives us a curve. Okay, this gives us a curve. So you can see here that there are three curves, 1, 2 and 3 curves, and they all represent different stages of erosion, river erosion, okay, or drainage basin erosion, that we will study in detail in upcoming slides. Okay, so yeah, so there are basically two ways of representing these hypsometric curves. Again, first one, where we are going to use the absolute value of elevation, okay, on the y-axis, and the absolute values of area in square kilometers. Okay, and how we are going to calculate these areas, that we will discuss further. And second, you can also take the proportion, okay, proportion of the elevation and proportion of the area and plot them respectively. Okay, so there are two ways of representing these hypsometric curves. If you are doing either of them, they both are correct. Yes, so how these proportions are actually calculated? Okay, so the method was given by Horton in 1932. So basically what we are doing, first we are finding H. For example, we divided our drainage basin into different elevations using contour lines. Okay, so these contour lines represent different elevation intervals. So for example, if I take the elevation at this point, then that will represent my H value. Okay, and the H and the capital H is the maximum height of the basin. Okay, so of course H will be constant, right, and small h will be variable. That will be calculated at different contour different contour points. Okay, contour lines. Okay, so this is how you calculate H, and when you divide H calculated at different points by the capital H, the maximum height, then you get this H by H proportion. And then comes your A by A. A is the area between consecutive pairs or successive pairs of contour lines determined by planimetry. So here you see there are two contour lines forming one area. Okay, so you calculate this area for small a, and your capital A is the total area of the drainage basin. So when you combine these two parameters at different points, you get such curves. Okay, now the another method, hypsometric analysis through hypsometric integral. Okay, so second method under hypsometric analysis is our hypsometric integral, which actually signifies the quantitatively expressed hypsometric analysis, and this represents the area under the hypsometric curve. Okay, and the value represents the how it represents, that we will see in upcoming slides. But here you have to understand this, that hi value represents the area under the hypsometric curve. Okay, and hi is expressed as a percentage. Okay, this is given as percentage, for example 60%, 70%, like that, and also an indicator of the remnant of the present volume as compared to the original volume of the basin. For example, if I say that hi value is 0.6, or let's say 60%, that means that of the total area of the drainage basin, only 60% is remnant. Okay, only 60% of the volume is remnant at present. Okay, so this is how your hi hi is used. And hi all in the same way, hi represents or indicates the erosion status of a watershed or a drainage basin. Okay, so if you see, this is the, let's say this is a horizontal plane, that was the 100%, and now you see only this much of area is left, or this much of volume is left. So if you calculate the hi, it will give you some value, and that value will represent the erosional stage of this particular drainage basin. Okay. Okay, so here let's combine hypsometric curves, stage of erosion, HI values and their significance. Okay, then here we are going to conclude it. Okay, so before that, how HI is calculated. So for HI, we take the mean elevation, subtract it from elevation minimum, and divide the entire by the difference between maximum and minimum elevation at some point. Okay, you can do this calculation for a single pixel as well. Pixel by pixel you can calculate this HI value and see the distribution, or find out, identify the patterns in your study area. Okay, that again we are going to learn in our upcoming series. Okay, now the type of hypsometric curve, convex upward. Okay, so if you see this curve here, this is convex upward curve. Okay, and it represents the youth stage of erosion. Why it represents the youth stage of erosion? Because you see the area under the curve is almost or greater than or equal to 60%. That means 60% of the area is still there to be eroded by a river. Okay, so this represents the youth stage of a landscape or some landform. Okay, so this represents and this is represented by a convex upward curve. And what is its significance? Stoller 1952 says that such areas are highly susceptible to erosion and is under development. Okay, there might be some tectonic activity going on which keeps on raising the landscape with time, and the rivers or river network is not, you can say, powerful enough to erode the entire area. Okay, it is not in equilibrium, you can say like that. Okay, now comes the S-shaped. You see this middle one, this is more S-shaped curve. Okay, and here the HI value is between 0.35 to 0.60. Okay, and that means the area or the remnant volume be below this curve should be between 0.35 or 35, only 35% to 60% of the area or the volume of the drainage basin is remaining. Okay, and such stage is called equilibrium or mature stage of erosion. Here the basin development has attained steady state. Okay, and when you have concave upward like this sort of graph, concave upwards, there the value will be less than equal to 0.35. That means only 35% of the volume is remaining. Okay, and such areas are called, such area shows monadnock or old stage of erosion. And here a basin is called as fully stabilized. Okay, and this is how this will look in your real landscapes. Okay, so you see youth stage, such sort of landscape can be visualized. This is your mature stage and this is your old stage where everything is eroded or most of the things are eroded. Okay, so when you go to the higher peaks of the Himalayas or higher ranges of the Himalayas, you will mostly find youth stage of erosion. Okay. Now, what is the importance of hypsometric analysis? First, it gives us that how much of the area is stabilized by erosion or not. Okay, in one word, right? And another thing, using this particular approach, by examining the shape and the structure of the hypsometric curves, one can gain insights into topographic characteristics, watershed management, erosion prediction, soil conservation, and urban planning. Okay, such approach helps in of course the approach or the importance is not limited to these 5 points, that it has many more importance. But to discuss here, to conclude here, such analysis are useful at these fields. Okay, in water management, erosion prediction. So people working in these fields can utilize this particular index to identify the stages of erosion in a particular drainage basin. Okay, so these are the literatures that I have taken help for presenting this, theory for preparing this theoretical background for hypsometric analysis. So now you can, if you have understood the concept of hypsometric analysis theoretically, you may go to the next video to learn step-by-step tutorial and step-by-step procedure on how to calculate the hypsometric curves and hypsometric integral using different type of data. Okay, so thank you, and subscribe our channel and press the bell icon to get the latest notification on our uploads. And I will keep posting the videos, the GIS educational videos um, frequently in upcoming days. Thank you.